this, basically. Okay, that's good. Okay. All right, thank you. Well, I'd like to thank Jorge and the other organizers for putting together what's been quite an interesting meeting so far about witnessing gravity in a lab, or quantum gravity in a lab. What I'd like to talk about now is work I've been doing with my group at Waterloo and with my collaborator Magdalena Zeik, who is at Stockholm. And it's about how we might think about an effect of quantum gravity that we expect without actually having a quantum theory of gravity. So let me begin with the quantum vacuum, which is a rather noisy place. We all know because of quantum effects that empty space is not empty. It's filled with quantum fields, electric fields, magnetic fields, scalar fields. And they're like a coupled set of springs, coupled springs, one at every point, and they fluctuate. They vibrate because they have 0-point motion. And the vacuum state, the ground state, is a global field state. So not only are there fluctuations at every point, the fluctuations here are correlated or entangled with fluctuations over there. And Summers and Werner showed quite a while ago that you can have a bell-like inequality that's violated by these local fluctuations. And somewhat later, it was pointed out that this entanglement in these field modes can be extracted. It was Anthony Valentini that first pointed out this effect, but nobody really paid much attention to it. Benny Resnick then, I think, independently looked at this idea in the context of a scalar field, which got a little bit of attention. Grant Salton, Nick Menicucci, and I took a look at this in quite a bit of detail now about, I guess, 9 years ago, though we started working on it 3 years earlier than that, to point out that you actually can swap entanglement from local field modes into devices idealized as quantum detectors, which are model systems that couple to quantum fields. And this use of these devices corresponds to what I call an operational approach to probing quantum fields specifically, or more generally to physics in general. The idea is, in an operational approach, is what we really understand about physics is what we learned from measurements using rods and clocks and detectors. So, for example, an atom, we know, can respond to an electromagnetic field, or a photon. If it absorbs a photon, the electron goes up an energy level, and when the atom emits a photon, the electron drops down a level. So theorists like me like to idealize this atom in terms of a qubit, also known as an Unruh DeWitt detector, which is basically an atom with two energy levels, a ground state and an excited state, and they're separated by some energy gap. And Bryce DeWitt, I think, was the person who actually first introduced this as a way of showing that the Unruh effect has measurable consequences in terms of such a device undergoing uniform acceleration would become thermally populated, or rather an ensemble of such devices. So I like to draw this thing as a little box. It's kind of like a quantum dot. It's a little device that has two energy levels. And the key quantity of interest is the probability, P, that the detector gets excited. There are other quantities of interest as well, but that's one of the main ones. And the typical model used for this is the following. In the vacuum state in curved space, you have the, where's this light? There we go. You have the scalar field in a curved space-time. You have a detector that's this two-level system, capital Q, and you have an interaction between the field and the detector, which can be taken to be a number of things, but most simply is taken to be a linear interaction along the world line of the detector, assuming a point-like detector, which is quite common in the discipline. And Shi and Lin and Baylock, who did a lot of work pioneering this kind of approach and looking at it in detail. It provides, as I said, an operational means of understanding the quantum character of space-time, in the sense that you probe the quantum field phi, but the behavior of the quantum field cares about the structure of the curved space-time. So you can, of course, put in many detectors, which has utility, typically 2, sometimes 3. So this is the same thing I wrote down before, except now I'm in a fully curved space. The Ricci scalar is up there in the first term, and it could be conformally coupled. The scalar field can be conformally coupled to the curvature, and there's the free scalar field, phi. And the interaction term turns out to be given by this simple expression in terms of raising and lowering operators of the field. This is called the monopole operator. So sigma plus takes you from ground to excited, and sigma minus takes you from excited to ground. I see I have a typo. The second thing should say sigma minus. And the switcher is simply something that allows the device to be turned on for a finite period of time. One of the features or bugs, depending on how you look at it, of something like the Unruh effect is that in its original formulation it was for a detector uniformly accelerating eternally. But of course no physical device can do that. So you can model the finiteness of the device with a switching function, commonly taken to be Gaussian, but this is basically a property of the device. There are other switchers that can and have been used. So the idea is you take some initial state, which would be the initial state of the detector or detectors, and the initial state of the quantum field, and you unitarily evolve it in the interaction picture. And then you get to a final state according to typical standard methods in quantum field theory. And then you trace over the field, because what we are interested in is the reduced density matrix of the detectors after they have interacted with the field for some finite period of time as governed by the switcher. So for a single detector, it's well known that you get this simple diagonal density matrix, 1 minus p and p, or p sub d, where p sub d is what we call the detector response function, and it's given by this integral over the 2-point correlator of the fields, the Whiteman function. And there's a lot of information in here. This quantity is sensitive to the motion of the detector. It's sensitive to the curvature of space-time. It's sensitive to the initial field state. Here I've put in the vacuum state, but you could imagine starting in, for example, a coherent state of the field or a thermal state or something else. And it's, of course, sensitive to the choice of quantum field, whether it's a scalar field or a vector field or a fermion or what have you. For this talk, I'll stick with scalar fields. So there are some key results that come out from this approach. One is that accelerating detectors get hot. So if you take one of these detectors and it accelerates, you find, as I said earlier, that either its rate of response or the response function over an ensemble is given by a thermal distribution whose temperature is proportional to the acceleration A multiplied by h bar over kbc. Kb is Boltzmann's constant. This is, of course, the celebrated Unruh effect as given in these classic references here. Another result in the field is that detector entanglement degrades. So suppose you have a pair of detectors and they are in an entangled state, and then one observer is undergoing acceleration with his or her detector, well, then you find that the entanglement degrades or declines as a function of the acceleration. This was shown by Yvette Fuentes and myself almost 20 years ago now. And this effect has been demonstrated in a number of ways, number of different kinds of fields, and so on. And then the last one that I mentioned earlier about extracting entanglement is that separable detectors become entangled upon interaction with a field, or rather can become entangled, as pointed out in these references here. So, I want to put a detector in superposition, and in fact, this is something that Eduardo Martin-Martinez and Yvette and I did about, 13 years ago, I guess now. And the idea was the following. Suppose you had some kind of detector and you set it through a beam splitter into a Mach-Zehnder type of interferometer, and you measured the phase difference at the end. Could you learn anything in this process? And what we had in mind was seeing if there were some way of maybe bringing the Unruh effect closer to experimentation, because those factors of h bar over kbc mean that you need accelerations of about 10 to the 21 centimeters per second squared to get 1 degree Kelvin, which of course is practically impossible. So what we did is the idea was you could place this thing into this MZI, and in one trajectory it would be inertial, but in another trajectory it's accelerated through the box, and you would compute the Berry phase around the loop. We showed that in fact there was a phase gained around this loop, and if you looked at this phase, or perhaps the phase difference between the accelerated trajectory and the inertial one, we did indeed show that you got, I see the fonts didn't quite come out right here, but for, you did get, oh boy, it really didn't, let's go backwards here. If you looked at the Berry phase around the loop, it would grow with acceleration. That was a very tiny amount, on the order of 10 to the minus 8. So it's a very tiny phase to measure, and what didn't come out on the axes is the magnitude of the acceleration was like about 10 to the 16. Now, 10 to the 16 centimeters per second squared is still pretty high, but it was on the order of a factor of 1,000,000 better. So this at least offered the hope that perhaps we could learn something by putting a detector in superposition that we otherwise could not learn. So a number of years later, Magdalena Zeik approached me and said, why don't we consider superposed detectors that are quantum controlled? So this is how I started working on this again. So there's the interaction part of the Hamiltonian for a single detector coupled to a scalar quantum field, and the response function P is given by the expression underneath it. So if you had a superposed detector, as in an MZI, you would basically have this kind of state. You'd have the qubit, or the UDW, coupled to some quantum ancilla that could be in one of two possible states, or many possible states if you wanted to have a multiple superposition, let's say over 3 paths, or 10 paths, or 1,000,000 paths. That's too many, I'm going to stick with 2. But this would be the interaction that you would have, and they would be regarded as control qubits. So if you measured this thing in the controlled state, the expression for P at the top of the screen would change into this one at the bottom of the screen. And if you notice what is there, that Wij term is summed over all possible trajectories, and in particular you get interference because you've got the interaction along path A, and the Whiteman function that's the correlator of the interaction along path A with the interaction along path B, something you do not get in the typical case. So in these papers, 3 trajectories were considered. The obvious thing to try first is to see what happens to the Unruh effect. So we considered trajectories that were superposed with parallel accelerations separated by a proper distance L. We also considered anti-parallel accelerations, and we considered accelerations of different magnitude but designed so they had the same Rindler wedge. Those double pictures you see are the different, or not double pictures, those 2 double diagonal lines you see in the first 2 pictures are the Rindler wedges of the 2 trajectories. So what we found is that once you measured the response of the detector at the end of this exercise, is that it did not exhibit the A over 2 pi temperature that is there for the Unruh effect. The interference actually changed that result. Superposed detectors with the same uniform acceleration don't have a thermal response. And here is a more complicated version. The upper of what I just said, the upper picture is for superposed parallel accelerations. So the energy gap is in the upper part. A negative energy gap means the detector starts in an excited state, so it changes how it decays depending on its acceleration. It's a bigger effect. That's why you look at it. The bottom axis cut off a bit is the proper time, a tau of the acceleration. It's really the acceleration times the proper times. It's a measure of acceleration. And if you take slices at these dashed lines, you see you get this wavy line, which is indicative of quantum interference. The anti-parallel case has a wave pattern, qualitatively the same, but quantitatively quite different. So the point is that a superposed detector gains information about the field. And so the next thing we looked at is to compare what would happen if you had a superposed detector in a thermal bath versus a superposed detector in a de Sitter space where the temperature of the bath was the same as the de Sitter temperature. Well, the detectors were separated by a distance L, which of course in the de Sitter case can't stay constant, but you can choose it to have the same separation at time 0. It was shown by Gibbons and Hawking that if you had one detector, you cannot distinguish between a thermal bath and a conformal vacuum of an expanding universe at the same temperature. So in other words, suppose one day you wake up and you're in a spacesuit and it's dark and it's empty and you don't know what happened to you. So you pull out your UDW detector and you see, oh my gosh, it's got a temperature. You can't know if you are in an expanding universe because aliens abandon you there, or if they have put you in an oven and cooking you for supper. It's one or the other. Neither is very attractive. But if you had an MZI with you and could put the detector in superposition, you would be able to tell whether you were lunch or whether you were just going to die all alone. I'll leave it to you to think which is better. So this led us to think about superposing space-time. We still lack a quantum theory of gravity. There's all kinds of ideas. They've been around now for 4 to 5 decades. While there's been some progress, I think it's fair to say there is not really any success. But one general expectation is that if everything quantum can be superposed, that's a generic feature. So it's reasonable to think that space-time can be superposed in some way. But how can we do this if we don't actually have a quantum theory of gravity? Well, here's one way of looking at it. And basically the logic is this. Superpositions of stationary detector trajectories in a single space-time can be mapped to a single detector in a superposition of diffeomorphic spacetimes. And here's an example. Suppose we had the de Sitter vacuum and the detector's in a ground state, but it's in a superposition of some location xi and some location xi plus L in de Sitter space. Well, I can write this as an operator that's the identity plus a translation operator in de Sitter space, but instead of having it act on the position state psi, under time evolution, I can have it act on the de Sitter vacuum. And effectively what I've done is superpose the de Sitter space. The unitary will care about whether it's in position xi or position xi plus L. You don't need to go to de Sitter space, of course. All I'm saying is that if you beam split something and have it go on two different trajectories, you get exactly the same picture if you keep one trajectory but in a superposed space-time shifted by a constant amount. So the second way is a bit awkward, perhaps, and you might wonder why you would do it. But so this is what, Magdalena and Josh Fu and I pointed out in this paper here a few years ago. So the superposed space-time that becomes interesting works in the following way. Here's the de Sitter hyperboloid, and you can imagine putting a detector at some particular angle on the hyperboloid relative to some axis, and then at some different angle. So theta 1 and theta 2. And you could have this detector superposed as it moves along the hyperboloid at two different angles. Now that's equivalent to having the two de Sitter hyperboloids in superposition where one's rotated relative to the other. But once you see the formalism, you can just say, well, what if the de Sitter spaces have two different curvatures, L1 and L2, or two different de Sitter lengths, L1 and L2? Then you genuinely get a superposition of spacetimes because these are different solutions to the Einstein equations because they have different curvatures. Now, we can't prove that this necessarily follows from a quantum theory of gravity, but it does seem, at least to me, to be a reasonable expectation of what one might get. Or put it another way, maybe someday somebody will come up with a quantum theory of gravity and show that this does not happen. Well, that would be very interesting, but it would also certainly run contrary, I think, to all expectation. So you do get different results. On the left is what you get when you angularly superpose, and again, you see another version of the effect I've said. The Planckian spectrum, when theta is 0, in other words, the superposition is on top, doesn't do anything interesting. Well, I guess it is interesting if you like the Unruh effect. But I mean, it just has the typical Planckian type spectrum that you get from that. But as the angles get larger and larger, which is what happens when you move down the screen, the lower curves, the response becomes quite different. It develops these kinds of oscillations. And notice again, this is for negative energy gap. The detector begins in an excited state. Way down here, there is a teeny tiny non-zero. Well, this thing just isn't. Where's the? Okay. Well, at the bottom, for positive gap, you get a non-zero value that's exponentially decaying. The curves are a little bit different, but very hard to distinguish there. On the right is a graph of the detector response for different ratios of the curvatures, and for some reason they were called R instead of L there, but it's basically the same idea. The farther away you get from unity, the less and less the response rate looks like the Planckian distribution. So the point is the following. Flat space superposition is equivalent to superposition of orthogonally translated Rindler trajectories. If you go to curve space, you can take this becomes a superposition of translated equal redshift trajectories in de Sitter, but you can then make what I think is a reasonable hypothesis to say that you can superpose de Sitter spacetimes having different curvatures. And when we did the study, we did this in such a way that we placed the detector so the temperatures were equal in the superpositions, even though the curvatures were not. And you do indeed get non-trivial interference. You do not get the de Sitter temperature. So what about flat space? Can you superpose that in an interesting way? Well, the answer is yes, if you cylindrically identify, let's say, one of the directions. Let's say with circumferences LA and LB. So I can play this same game where I superpose the unitary operator, one for LA, one for LB. In other words, the quantum control parameter is the radius of the cylinder, or the identification length in the Z direction. And the interaction Hamiltonian is just like what I showed you earlier between with the monopole operator in the field operator at the detector location, the switching function, the coupling constant. But there's the quantum control, the radii of the cylindrical identification. So we took a look at this. Josh Foos, Shabila Arabache, former master's student, and Magdalena, and me. And what we found is that the detector response exhibits this phenomenon similar to what I showed you in de Sitter. Again, note the gap is negative. The detector starts out positive. You can see for detector starts out in an excited state. You can see for positive gap that there is an exponential fall off, but there is a distinction between the different cylindrical identifications. And you get this step kind of function. More recently, I just put out a paper with Lakshay Goyal, Everett Patterson, Maria Prasadio-Rivas, Madi Torbett, and Naya Chef-Shorty, where we had them accelerate along the x direction in superposition. And the higher the acceleration, the more these step function patterns get smoothed out, as you can see in this repeating video graph of how it changes from zero acceleration to non-zero. So certainly, again, the superposition provides us with correlation information that would otherwise be lacking. So to finish this off, let me talk about black hole superposition. Can we put a black hole in superposition? Now, in general, this is a complicated operation. In principle, of course, you could just take your favorite black hole and apply this formalism to it, but the problem is in computing the Whiteman function. The Whiteman function in a general black hole, as far as I'm aware, can only be computed by doing a mode sum over the fields, and this is painful. But there's one black hole for which the Whiteman function is simple, and that's the Banyatos-Teitelbaum-Zanelli BTZ black hole, as it's called. It's a black hole in 2+1 dimensions that has constant curvature. So we already learned something about how to superpose constant curvature de Sitter spacetimes, so we thought, let's do this for negative constant curvature for the black hole. So how does this work? Well, I'd already done some work with now former students Laura Henderson, Roby Hennigar, Alex Smith, and a collaborator, Johnny Zhang, and in another paper in 3+1 with Keith Eng and Eduardo Martin Martinez. And basically, we took in these papers, we put two detectors, not superposed yet, two detectors in de Sitter space and looked at how they harvested entanglement as they were allowed to evolve over a finite period of time. But using that knowledge, we then can go to the case using the previous quantum reference frame formalism to superposing the two spacetimes with a single detector there. So this is what we looked at in this paper, except I don't want any de Sitter space, I want a black hole. So how does that work? Well, some of you may be familiar with this, but if you're not, the idea is the following. Anti-de Sitter space-time can be mathematically written as an hyperboloid given by the top equation in the yellow box, constrained to live in a flat space with two time-like directions. So I drew the hyperboloid in the only case I know how to draw it, which is in 2 + 1. And there are the two time-like directions in the space. So ADS is that hyperboloid. So when you insert the first equation into that metric, you lose, of course, a coordinate degree of freedom, and you end up getting this metric that I've written below, and that's d-dimensional anti-de Sitter space, where the cosmological constant is given by this factor 1/L² times these dimensional parameters. So in 2 + 1 dimensions, the angular part is just d phi squared. So that's 2 + 1 ADS. Now, identified anti-de Sitter space is a black hole. So there's that same covering space metric, that higher dimensional flat space with two time-like directions and the hyperbolic constraint surface. But now if I make this kind of transformation, I end up getting this metric. Now you might say, Rob, that's still ADS. Well, it is, but not quite the same ADS. If phi is unidentified, this is ADS Rindler space. It's what you would write down. It's the coordinate system a uniformly accelerating observer would use in ADS. However, if you identify the phi direction, then you get a black hole, where the quantity m is the mass of the black hole. So you can rescale these parameters, and then you get this metric where phi tilde has the usual 0 to 2 pi periodicity. So that is the BTZ black hole. Was shown to be a legitimate black hole in 1992 by Bagnatos, Teitelbaum, and Zanelli. So here's a picture of it that I took from this paper by Arias Henriquez, Ruth Gregory, and Andrew Scoynes. And what this cylinder is the Einstein cylinder, where you can formally compactify ADS and you can map it to an Einstein cylinder. Time goes vertically. So lines of constant t are the black lines you see in the picture. The blue lines are lines of constant angle. The orange dotted lines are lines of constant r. The identification is the red line. So what you would do is you take a Rindler slice out of this cylinder and identify the red line on the left with the red line on the right, and the green line is the bifurcation surface or the horizon. So if you want to think geometrically about it, that's what it looks like. So the superposed BTZ black hole would basically be obtained by taking those two things and putting them in superposition. One with identification MA, the other with identification MB. And that's what we did. So, how does this work? Well, the Whiteman function is still given by these conformal quantum conformal scalar field. The reason why we use a quantum conformal scalar field is the Whiteman function is given in terms of this geometric quantity written for ADS in terms of the sigma of xx prime, where sigma is the geodesic length between the 2 points x and x prime in the phis. I suppose I should have written down what sigma is. It has an explicit expression. But anyway, that's why it's so nice. There's no mode sum here. For the BTZ case, you impose the identifications, here symbolized by gamma, and you sum over all of them. And you can put either twisted or untwisted boundary conditions on the scalar. We always do untwisted, but if you want, you can do twisted. The parameter zeta corresponds to the boundary conditions at infinity for the scalar. 1 for Dirichlet, 0 for transparent, and -1 for Neumann. So in the superposed BTZ case, instead of having the same gamma, we have two different gammas, one for space-time A, the other for space-time B, and we sum over all the possibilities. So it'll be AA, AB, BA, and BB. So basically what we've got is a superposition of a black hole of mass m, A, and a black hole of mass mb. With these two different identifications, they're the gammas. And the superposed Whiteman function will look like this. So under the dynamical evolution that I described, you get this unitary evolution, and then we condition on either the plus or the minus state, MA plus MB or MA minus MB, and trace out the field. And what you get are the sum of these two terms. There is, in the reduced density matrix of the detector, there is a PG term, the green one, and a probability it'll get excited. And what makes it differ from the usual case is this interference term, LAB, in the case of the excited one, and these time-dependent oscillations, which is what you always get in a quantum system when you superpose two different energies. The probability oscillates in a time-dependent way. So that's standard quantum. So here's what we get when we take this, let's say at some fixed time. We find that as so on the vertical axis is the response function. On the horizontal axis is the ratio of the square root of MA over MB. And what we see is we get spikes that are occurring at rational values of root MA over MB. There are resonant peaks at those values, which are very reminiscent of Bekenstein's black hole mass quantization conjecture. The upper graph is when we condition on the plus-minus states. The lower graph is when we condition on MA plus IMB or MA minus IMB, and it's color-coded so that you can see what it is. So in the plus-minus states, we get a big spike at 1. We get full cancellation if we condition on the one where there's a 90-degree phase difference. We've also recently done this with rotating black holes. This was done with the same collaborators, plus Sendikiwan Suryamada and Matthew Robbins. And here's one graph. We have a number in this paper. But basically, the point is, for all three boundary conditions, we find that we get these spikes at rational values of the horizon radii. Again, reminiscent of Bekenstein's conjecture. So what would a superposed metric mean? Well, classically, if you know the geodesic separation between 2 points, you can take this double derivative and then take the coincidence limit and obtain a metric. So Akim Kempf and Mehdi Saravani and Ezenbeigi showed, or suggested, they didn't show, but they proposed that maybe the way to understand a quantum metric is to take this same double derivative coincident limit of the Whiteman function. And he has been looking at that in a variety of ways. So that may very well be how we could understand what a quantum mechanical metric would be in this picture. So in the case of the superposed black hole metric, we would do something like this. Now, I have not pursued this any further, but I'm putting it up on the screen to show you that there is perhaps a way of thinking about this that could make sense. So in the remaining couple of minutes, this is about witnessing gravity in the lab. How would you do it? Well, step one, make a UDW detector. This has already been proposed by a group at Nottingham in this paper from 4 years ago. And the idea is that you take a laser, put it through a filter that, well, you first detune it in a modulator, put it through a filter that cuts out the central band, and then the high frequency band is like the excited state of the UDW, the low frequency is like the ground state, and then their idea is to put it through a rapidly rotating disk that has a hole in it, so that this would correspond to circularly accelerating the detector, and then it goes through a BEC, and the surface fluctuations of the BEC play the role of the quantum vacuum, and the hope is they will measure the circular Unruh effect. So when I heard about this, I went to Silke Weinfurten, and I said, well, if you're going to make one, how tough is it to make two? And let's make two and see if we can extract vacuum entanglement or do entanglement harvesting here. So now we'll have two detectors. We don't need to put them through that circular filter. We could if we wanted. What we want to do is see what the correlations are between two initially uncorrelated detectors to see if the correlations in the BEC surface fluctuations get imprinted into these lasers. Well, step 3 would be to beam split a single one of these things, assuming you can get the first thing to work. And then the goal here would be to actually measure the response of a superposed UDW and see if it does what this theory said it should do. And then step 4 will be to superpose two BECs to simulate a space-time superposition. Now, I don't know how to do that. Of course, I'm a theorist. I don't really know how to do any of the other steps directly. But maybe, this is possible. So I'm going to stop here and just point out that there is a mechanism for constructing superposed spacetimes even though we don't have a quantum theory of gravity. We've done it for several examples: flat space, de Sitter space, the black hole. We can understand, it's not a matter of just superposing. We actually have a method for determining the physical implications or physical effects of these things via these detectors. So there's lots of spacetimes. Feel free to try your own and do this. What we're finding is that we've got, at least for the simple black holes that I've talked about, responses that seem consistent with Bekenstein's area quantization conjecture. This provides a pathway, I think, for understanding the effects of quantum gravity phenomenon even though we don't have a quantum theory of gravity. Somewhat the way Niels Bohr proposed a model for the atom without a full quantum theory, I think this is in the same spirit. Can we witness this in the lab? Well, I hope there are some experimentalists listening that would be able to figure out how. Thanks for your attention.
All right, questions?
I wonder if there's an simpler electromagnetic analog of this case where you have a superposition of charges and, coupled to an electromagnetic field, and can you view, does it just follow from QED?
That's a very good question, and one worth thinking about it. You're asking the question I love to ask, so I should put my money where my mouth is and do it for electromagnetism. Something's got to happen, presumably. You could put the electromagnetic field in a state of superposition. We know how to do that, but you'd want it for a larger scale field, superposition of coherent states. But yeah, I think something similar should happen. Yeah.
Thanks. This was a really, really, really interesting and thought-provoking talk. I mean, the whole superposition issue. I have to say that, I mean, if you look at the seminal paper from Ted Jacobson in the 90s, who derived the Einstein equation from the area relation that you're talking about, everything sort of holds together. I mean, you know, if it turns out that you can interpret area as an entropy and plug it into the Raychaudhuri equation and get an Einstein equation out, this was the Jacobson's paper. Now, as you're saying, your results are consistent. If you change curvature, you change if you change curvature, you change temperature. I mean, you extend this to a sort of, from just a thermal bath to a thermal bath coupled to a probe. However, I mean, just as a sort of, from a fundamental quantum mechanics perspective, I can see the two detectors superimposed in the same geometry and related by a unitary transformation. But two detectors superimposed to two different thermal baths with two different entropy contents sort of goes against the basic formalism of quantum mechanics, right? I mean, a detector is a macroscopic object. You can forget about it and create two superpositions as long as you're, but a superposition of two entropies is inconsistent with both quantum mechanics and statistical mechanics. I am skeptical about this Akim Kempf and company proposal because of this reason, but yeah.
Well,
anyway.
So you want me to comment, or?
Sure.
Okay, so to a certain extent, I have assumed macroscopic quantum superposition, though I'm not required. There's nothing that says, for example, these black holes have to be macroscopic objects. They could be microscopic, so in principle, there's no reason why I think that could not happen. There is a paper by Czeslaw Bruckner and collaborators where they use the quantum reference frame formalism to show that you can make sense out of superposed thermal baths. So I would probably refer you to that, though I can't remember the specific reference number at the moment. But there is this, I probably should have given Czeslaw and his group more credit. Basically, this is to some extent rooted in that formalism that any reference frame is also, in effect, a physical thing, right? A physical rod, a physical clock, and therefore it should be subject to quantum rules and should be quantum superposable. And out of this grew the formalism of quantum reference frames that to some extent we have, well, to some extent that we have employed here. So that's probably what I would say for that.
Thank you very much for this very interesting talk. So I would like you to comment about the following line of thought. Because what we understand by space-time are classical solutions of classical Einstein equations, and we don't superpose classical stuff. How confident are you that the idea of superposing classical space-times would be promising? I mean, I understand, I believe that, you know, space-time eventually is going to be described by some quantum structure, and that this quantum structure as a quantum thing, can be in superposition, but we're talking about a classical view of a space-time that we have at the moment, that is a manifold endowed with a metric, classical metric. So how promising you think that this idea of superposing classical space-times can end up describing nature? That's
well, I mean, that's an interesting question. I guess I would say I've implicitly assumed, for example, in the case of a de Sitter space, that the different values of the curvature, basically, that any given value of the curvature corresponds to a state in the Hilbert space for the de Sitter. So you've got, I guess, continuously infinitely many of them. And if you believe that, I guess I don't see why this couldn't work. We have coherent states, and they can be superposed. I mean, are they classical? I would say they sort of are, at least they're close. So, but it's a good question. It may very well be that when we find a quantum theory of gravity, that we'll discover that whatever it is that leads us to the classical limit of a space-time forbids the kind of superposition I'm doing. I have to admit that's possible. I hope not, but it's possible. You're quite right. However, I think we should look in this direction. I think we might as well see what this tells us. But I would agree with you to the extent it may be that the real quantum theory of gravity that I'm sure one of the people at the back will find next week will tell us something different. Yeah.
Professor, thank you for the talk. I have a couple of questions. On the Galton's point, this harvesting entanglement protocol was developed on QED formulas, like the Valentini's original paper was a QED argument. So someone has like tested this? Is this a thing that people do it in the?
Well, to my knowledge, never directly.
But it should be possible, right?
Yes,
okay.
That's right.
So thank
but
you.
But it's so there is there's a set of experiments by a group in Zurich, Jerome Feist's group, and they what they do is they take a zinc telluride crystal and they cool it down to about 4 Kelvin. And the idea is that that puts the crystal in the ground state, and the ground state of the crystal plays the role of the quantum vacuum. And they have been able to show, this is a real experiment done in the real world, really, they've been able to show that laser pulses can probe the Whiteman function of the vacuum state. They basically send in polarized laser pulses, I think along 2 different axes, and then they're rotated, and then that probes the Whiteman function. So there's a proposal that in a paper that came out, I think late last year, but I think it just appeared in PRA, where they're proposing to do entanglement harvesting using this electro-optical sampling, where you will send in 2 different laser pulses that are uncorrelated into this zinc crystal, and then from that, the correlations will tell you this. So I say it really is close to being done for real.
And let's thank again the speaker. And let's go for lunch. We meet here again at 2.